Hi, I'm Michael DeBellis, and I'm going to be talking about research I did with George Gino, Adarsh Balaji, and Jacob Gino recently on modeling climate obstruction with a neurosymbolic architecture. Um, the reason for this presentation is that I wanted to make a presentation that was a bit longer than the ones that we did for two papers that were recently published. And as a result, this presentation is actually going to be divided into two parts. This is the first part, and in this one, I'm going to go through um, the terms and the technology, and then in the second video, I'm going to go over an example, how we modeled the climate obstruction theories, and then finally talk about next steps, acknowledgements, and references. So to begin, let's define some terms. So what is climate obstruction? Um, Climate obstruction is a response to a common trope that is in both the media and unfortunately even a fair amount of scholarly research that says that the main reason the public doesn't understand the significance and the imminence of climate change is due to poor science communication. Um, and in response to this, some social scientists have gotten together and formed the Climate Social Science Network, which I'm a member of as well. And they've developed an alternative hypothesis that they call climate obstruction. And this hypothesis is that the primary reason people don't appreciate the importance of climate change is due to propaganda funded by corporations with vested interest in blocking action on climate change. As part of this research, the CSSN has created and they also utilize several large online databases, and I've got three of them here in screen prints from three of them here on this slide. And as I was reading through the literature, it occurred to me, one, wouldn't it be really good to take all these different websites and integrate them into one common repository? And then two, wouldn't it be good to then take a large language model and use that as the front end to this integrated repository? And the reason for that second feature is that most of these sites actually have no search capability at all. The best you can do is like they are all pretty well structured. So you can navigate by going down various topics and go and then do like a control F on the page, and that's about it. There are a few where you could actually do queries, where you fill in a few fields like the name of a corporation, the date when, for example, like climate litigation, when the dates you're looking for litigation, and a few others like that. But the advantage of having a large language model as a front end is you can do all of those kinds of queries with a large language model, and you can do a lot more kinds of queries with a large language model. So that was our first goal, is to take these data sources, integrate them, and then use a large language model as the way to search through this integrated repository. Our second goal, more ambitious, is to integrate and create formal models of the climate obstruction theory. So if you're familiar with my work, you may know that like one of my goals is to use technologies like the web ontology language to make the social sciences, or what some people call the soft sciences, a little more rigorous. So in my opinion, one frequent issue with theories in the social sciences is that they aren't completely rigorous. So you can read a paper and get an idea of what something means, but it's not the same as like when you're reading a physics paper, or even like a computer science paper that's got logical statements or formulas, which are very unambiguous. And I think a step in the right direction would be to create formal models of some of these social science theories, and that's something that I've done a bit in the work that I've done with the semantic web, and that was our secondary goal for this project. So that's what climate obstruction is. So what is a neurosymbolic architecture? Well, it's a fancy term, but it's actually a pretty simple idea. What it really is simply taking two different kinds of databases and smushing them together. The first kind of database is a vector database, and Pinecone, some may be familiar to some of you. That's probably one of the best known purely vector databases. Vector database is something that you utilize for doing machine learning and large language models, because vectors are one kind of data structure that you use a lot with these kinds of systems. And you may be wondering, well, why do you even need a special database for vectors? Because, for example, in a knowledge graph, which is the other kind of database that is part of a neurosymbolic architecture, you have predefined data types, and you can have things like lists in Python or one-dimensional arrays, and those can be used to model vectors. But the thing is, the vectors that we're talking about that are stored in databases like Pinecone, these are not 100 list with 100 elements or even 1,000 elements, but list with like vectors with thousands of elements in them. And the way you use these vectors is not by just searching or simple operations, but you have to do fairly complex linear algebra operations like multiplying a vector times a matrix or a tensor, and to get efficient productivity out of these kind of vectors, you need to store them in a specific way, that's why there are vector databases. And so what neurosymbolic architecture does is it takes vector databases and it takes knowledge graphs and it brings them together. And the most common type of architecture right now that is built with neurosymbolic architectures is Retrieval Augmented Generation, or RAG. So RAG is an architecture that enables you to still use the natural language processing power of large language models, but it avoids the two biggest problems with LLMs, which are hallucinations and black box reasoning. And the way RAG avoids both of these is by using explicit knowledge representation, which is what an LLM does not have. In fact, there's a really interesting paper by the guys from DeepMind where they tried to do experiments where they tried to re-engineer, where are facts, like they took an example fact of Michael Jordan is a basketball player. Where is that stored in a large language model? And they found that literally it could not be done with the current large language models. So it's an unsolved, it's not that it's hard, it's that it's an unsolved problem. So large language models, as great as and powerful as they have this one big weakness, which is that they are as far from explicit knowledge representation as you can possibly get. I mean, even an assembler program has more explicit knowledge representation than an LLM, because even in an assembler program, well, if you know assembler, you can eventually figure out where things happen and why things happen. And so the RAG architecture, it gets around this problem by doing explicit knowledge representation. Namely, it will have a corpus of documents that are dedicated to usually one specific domain. And it uses that corpus of documents and only that corpus of documents to answer all questions. And so, like most architectural decisions, this is a trade-off. So with the RAG, you're getting a much narrower coverage of domains than an LLM. An LLM, you can ask questions like, what's a good recipe for chocolate chip cookies? And it'll probably give you a good answer. You can also ask the RAG questions about climate obstruction, and it will also usually give you pretty good answers. So I'm sorry, you ask an LLM, and then it'll also give you good questions. With the RAG, you have to focus on a specific domain. So in our case, we focus on the domain of climate obstruction. And if you ask the RAG about a good recipe for chocolate chip cookies, it's just going to say it doesn't know. And by the way, and that's the other big difference between a RAG and an LLM. An LLM will never say it doesn't know because it doesn't know what it knows. In other words, because it doesn't have explicit knowledge representation, it has no way to gauge, how good of an answer do I have for any specific question. Whereas a RAG does have that kind of information. And in fact, a RAG will, for most of the questions that you would ask an LLM, that are outside the domain, a RAG is going to just say, I don't know. But for the ones that you do ask the RAG that's in the appropriate domain, not only will it give you an answer, but it will tend to give you answers that are, it will give you answers that don't have hallucinations and that are not black box that are not black boxes, because it has this corpus of documents. It can measure how close your question is to the information in the document corpus, and then it will use specific documents from the corpus that were the closest match to your question, assuming there were any, to answer those questions, and it will return those documents as well to show you this is how I got the answer. So it gets rid of hallucinations, and it's not a black box, which of course is not to say that you can't get errors with RAG, right? So in other words, if you have a corpus with a bunch of documents that are terrible, that just have wrong information, garbage in, garbage out, that's always going to be a problem. But hallucinations are a very specific kind of error that are unique to LLMs. And with a RAG, you will not get hallucinations, and you will always get a justification. So it's never a black box. Okay, so now I've defined the terminology. Next, I'm going to give an overview of the technology we used. I'm going to talk specifically about the data pipeline we used to populate the RAG, and I'm going to talk about how we generate vectors, and then I'm going to show a data flow diagram for the architecture we use at runtime. So first of all, the technology that we utilized. To begin with, we used the W3C standard languages for the semantic web, the web ontology language, OWL, RDF and RDFS for the graph, the Sparkle query language for doing queries. For our tools, we used Python as our programming language. We use Protege, an open source tool from Stanford that's probably the premier ontology editing tool that there is to create the initial ontology. Then we used AllegroGraph to read in the ontology and then read in large amounts of data on top of the ontology. So Protege essentially gives you the ontology. AllegroGraph gives you the knowledge graph, which is the ontology, what people call the T-box, as well as the lots of instances, what people in the community call the A-box. And AllegroGraph was also our platform for the neurosymbolic architecture because, as with all major knowledge graph vendors, AllegroGraph has now integrated a vector database capability that is similar to databases such as Pinecone. And as I mentioned, we also used the Python client for AllegroGraph. That gave us access to a lot of those wonderful Python libraries. So like, for example, we use something called Beautiful Soup to do the web scraping, Streamlit.io to do the user interface, and a bunch of other tools I won't go into here. And then finally, for our large language model, we used ChatGPT. And then for our vocabularies, for metadata, we used SCAS, which is W3C standard, and Dublin Core, which is even older than the semantic web, very standard for metadata. And then we use the GIST upper model from Cambridge Semantics as a starting point for the ontology concepts in general. So GIST gives you a really nice, overview of the kinds of classes that you're going to want in most business and engineering ontologies. Things like events, people, organizations, commitments, and so on. So this diagram shows the data pipeline for processing documents and putting them into the corpus for the RAG. So step one is to do web scraping. So again, using Beautiful Soup, we extract documents and metadata, and we put those into a CSV file. So each row in the CSV file is going to represent a new instance of the document class, and each column in the CSV file is going to represent a data property. And then we take that CSV file and we load it into the knowledge graph via one Python function. Now, this yields what I would call a fairly boring kind of object at first, because as I mentioned, we only load data properties. So mostly strings, but sometimes we'll have things like, an XSD date time, or other, maybe a Boolean, other types of data types, but never object properties. We start by just bringing everything in as literals, either strings or other kinds of simple data properties. Okay, that's step two. Then step three is we take the data, a subset of the data properties that we just entered. Those are the data properties that have strings that make up the various documents. And also there's other data properties that are relevant as well. And essentially any data property that has a string that we want the LLM to potentially use to generate answers, we create a vector for all the values of that data property. And I'll show you that interface in a minute. Allegro Graph gives you a nice little interface where you can just go and list each data property that you want to create a vector for. Okay, so that's step three. And then the final step, step four, is we do post-processing that transforms this boring object which just has data properties into more interesting objects. Sometimes people call this a term I like, which is going from strings to things. So in other words, we're taking that boring object and we're analyzing some of those data properties, and we're saying, okay, well, we can take this data. And so an example of this is there will be a data property that represents metadata called the author string. And that will be a string which is delimited by semicolons. And then within each value that is delimited by the semicolon, there'll be last name, comma, first name, of the author. And so what we do is we process each of those strings. We first find divided into each one of the first and last names. We then look up in the knowledge graph and see, is there already an instance of the person class, with that first and last name? And we do various kinds of broad matching, so that we will find things like if it's the same name, but for capitalization may be different, or middle initial or something like that. Actually, we use a Python library that is specifically designed to parse last names. And as a result, we then look into the knowledge graph, as I said, and if there is an instance of that person already, then we use that instance. If there isn't, then we create a new instance, and then we make that instance of the person class, in other words, the author, the value of the has author object property with the domain, the starting point of the document, and then it points to the value is going to be each object that is an author. And that's just one example. There are many, many other and these are all kind of, ad hoc additional transformations we do of taking the data properties and turning them into objects and object properties. So if you recall, I mentioned that one of the steps in the data pipeline is that we wanted to tell Allegro Graph, here are the specific data properties with strings that we want you to use, and we want you to go and find the value of each one of these strings and generate a vector for it, put it in the integrated neurosymbolic knowledge base. And in addition, make sure there's a pointer from the vector to the appropriate document object and from the document object to the appropriate vector. And so you can see here, if you look at in about the middle there where it says new or existing, you have to tell it the vector database you're going to use. Below that, you have to tell it, which embedder you're going to use. We always use OpenAI, and then OpenAI has several different models. The best model, at least when we did this work, was the text embedding 3 large model. It's a fraction more expensive, but at the level that we're working, it was trivial. So we always use the text embedding 3 large model. The next field to the right there is the OpenAI key, which of course is obscured, for security reasons. And then below that, you can see, and of course it's scrollable. So there's about 20 or so data properties that we create vectors for, and you're only seeing like the first 4 or so. And in fact, most of them, the actual IRI is so long that you're not seeing the complete IRI, but you can at least see the one complete IRI up there at the top, which is from Dublin Core. It's the abstract metadata property, and obviously you're going to want to create a vector that represents the meaning of the abstract for every document. So this is the interface we use to create vectors for all of the different data properties that we want to have vectors for. Then the final step then is this is the runtime architecture. So now that those previous steps were, this is the way we set up the corpus. This step is what happens at runtime. So step 1 is that the user asks a question. That goes into the Streamlit user interface. And then that goes to step 2, which is a vector is generated for the question using the same model as the document corpus, because we want to compare the vector question to the vectors for the corpus documents. And step 3 is we do that comparison with a cosine distance function that finds vectors that are within the nearest neighbors to the question within a threshold defined by a parameter that you can configure. And this is an example of one of those linear algebra type mathematical operations where you need to have efficient representation of the vectors in order to do efficient kinds of operations like these cosine distance functions. Then if we don't find any vectors in the corpus that are within the threshold defined by our parameter, then it fails. And the RAG just says, I can't answer that question. And we may then go back and tweak the parameters. And I'll, in the second video, I'll show you the interface for how that looks. But if it does work, if we do find one or more documents in the corpus that are within the threshold of semantic closeness between the question and the corpus vectors, then we send the question vector, the string, and then the nearest neighbors that were within that threshold and those strings as well, all to ChatGPT. Again, this all goes on underneath the hood. It's all done for you by an extension to Sparkle from Allegro Graph. that calls the OpenAI API. Then step 5 is the OpenAI API returns an answer generated by the GPT-4 API. And by the way, so this is what is meant by retrieval augmented generation. So in other words, we're augmenting the prompt, just the user's question, with additional things, namely a vector that represents the prompt and the vectors and strings that were relevant that we found in our corpus. And we're sending all that to the LLM and telling it to use those as opposed to its own internal knowledge, which is a black box, as a way to avoid the hallucinations and black box reasoning. Okay, so then step 5 is we get the answer from the OpenAI API. We show that to the user as well as showing the specific strings from each one of the documents that we used for the answer. And then an additional option that we can use, and now this has nothing to do with the LLM, is there are often additional objects that we set up in the Sparkle query that we think are going to be good entry points to browsing the knowledge graph to find additional context about the specific topic that you're asking. And we can use the Gruff tool from Allegro Graph. Gruff is a great tool where you can give it a Sparkle query, take the results, and then it will automatically generate a network graph for you. And then Gruff gives you like so many ways to then manipulate the graph. Honestly, it can be a little bit intimidating because there really are so many ways. At first, you just see these huge menus, but after a while, once you start to use it, it's really exciting because it gives you such power when especially when you've got a large knowledge graph, to really explore it in many, many different ways. And you'll see an example of that, when I do the actual example. Okay, so that's the first part of the video, and I'll end here, and then I'm going to pick it up and finish in part 2. Thank you.